as we said again, if you have questions at any time, you can ask. So these lectures, we are going to focus we are going to focus on understanding what machine learning algorithms do, not how they work mathematically, not how they work mathematically. As we said earlier, this is data science class. If it's a machine learning class, we are even going to cover maybe two or not more than three algorithms. Depends the type of algorithm. Some of the algorithms are shorter in terms of their mathematics background. Some are a little bit complex or longer. Yeah, so need more time to explain. So here we're trying to cover almost all the major machine learning algorithm in less than 1 hour. So we're just going to talk what the machine algorithms are, but not how they work mathematically, I would say. So we are going to, that's all we're going to say here. Yeah, or let's see if any question. So hopefully by the end of this section, students, or we're going to be able to talk, I would say talk intelligently about algorithm, explain them to non-technical stakeholders. And also maybe we can justify why one algorithm is chosen over another in a real project. Mathematically, no, but we get the concept together. Yeah. So here we say, what is machine learning algorithm? And here we say machine learning algorithm is a procedure that learns pattern from data, also make predictions or decision without explicit programming. So algorithm improve performance as they see more data and they convert data to patterns. And hopefully from there we get our again prediction. So again, machine learning in general is a branch of artificial intelligence that focus on developing models and algorithms that lead or that let computers learn from data without being explicitly programmed for every task. So I would say in a simple words, machine learning teaches the system to think and understand like humans by learning from what? From data. Learning from data. Maybe that's all we can say here. Or let's see if any question yeah, in there. And also I would say that the main concept here is a set of rules or patterns that computer can follow to learn from the data. And this is where our algorithms will come in. For example, decision tree have its own rules, support vectors have its own rules and process of, again, identify knowledge from data or learning patterns from, again, data set. So the whole goal here, again, to move from input data to I would say an accurate prediction. Again, there's no silver bullet. There's no any 100% one algorithm is better than other. So we may see that in the future that sometimes depends on the type of problem you have and also the size of the data and also a lot of experience, try and error experience. And we may say one algorithm is better than other. But there are some algorithms that researchers have already tell us they are good. For example, I want to do decision tree. Most likely I will use random forest. Always random forest performs better than decision tree. Random forest is a assembly method. In this case, you may have like 20, you may select how many trees you want. That's why it's called forest, random forest. Again, I don't want to go detail, but sometimes depend. We can find the average of all of them, or we find a mode, a majority vote to get the right one. Assembly method use the concept of bagging and also boosting. Boosting. Random forest use bagging method. We'll come there, we'll talk a little bit. But the reason I'm giving this example is that most researchers or many papers tell us random forests perform better. Even assembly method, they perform better than comparing to, for example, decision tree with random. Now, the bagging can be any algorithms, but random forests use trees, but it's a bagging method. Yeah. Then, as we said, we have the boosting also, etc. Yeah. So yeah, so I would say that as we said earlier, the goal again is to move from an input data to accurate prediction, possible 100%. Yeah. So next question is why so many algorithms? Here I can say actually let's see different that's what I'm trying to explain. Different problems require different tools. So you may have different type of data. Maybe a structured data may work with different algorithm, unstructured data, or your data is very small. Maybe decision tree is good for small data set. Does neural network good for small data set? Maybe no, maybe large data. Or neural network is more robust. It can handle noisy data. So if you know your data, you are not perfect. I mean, first of all, we'll do the data preparation, everything, but here we are trying to say that some algorithms are very robust in terms of the type of data we have, if there's error, etc. Yeah. Also, another nice one, linear versus complex relationships. I'm doing regression. First, I will do some work. And let's say I'm doing a farming work. And the farming work, I came up with a fertilizer. And I'm not a farmer, but I'm trying to explain some concepts here. And this fertilizer, there's a outcome of is good or bad, is good or bad. And we generate some data on it. And I'm doing farming, the same farming. I also want to predict the price of maybe my product or the profit I'll make in the future. Now, I'll use regression. That's okay. About the fertilizer, my outcome is only yes or no, one or zero, one or zero. So should I use a linear regression or logistic regression? I'll use a logistic regression for that because it's only yes and no. Then when it comes to predicting the price of the product or future profit, here we have a comparison of we can fall any amount. Okay, here I'm going to use linear, simply, no, let's say multiple linear regression, more than one attribute. If it's only one attribute, maybe simple linear regression. So yeah. So what I'm trying to explain is that every algorithm depends on the type of problem. Even within the supervised learning, I may decided to use decision tree instead of support vector machine. I know the reason why. We may know the reason why. Maybe the size of the data or so. Now, if I'm using support vector machine, okay, support vector machine, the theory is nice. You know, we have the support, the vectors. Support vector machine, the algorithm will give us the boundary and the boundary, you have a lot of data, but only the data that are close to the boundary area to separate the two, good or bad, yes or true, or is those are the data that are more important. And actually, we call them support vectors. So the rest of the data far away from the boundary, they don't make any. They don't. Their decision is not. They don't make a decision to get the prediction or the boundary to characterize the, should I use the word? No, not or to classify. So yes, classify positive or negative. Only those within the boundary will make that, which we call the support vectors. So again, why I'm mentioning all this is that there, there are so many algorithms, but the problem, choosing algorithm most likely will depend on the size of the data, the type of problem, even the data types also. Is it a categorical, majority, or numerical value? Yeah. And the last thing we will mention here is that no single algorithm works best for every problem. You see, different size of the data set. So there are many, many reasons. Let's wait for a few seconds, see if any question, ask question. Same as I said earlier, the Columbia University professor said on YouTube. So prediction, as an example I can give is that we can have a house price predicted or sales forecast. Categorical, we can say spam or no, not a spam, like email. Grouping things, maybe customer segmentation. So again, if I'm going to group things together, for example, in terms of customer segmentation, good value customer, bad value customer. What type of algorithm? Should I use multiple linear regression? Maybe no. Maybe no. So it depends. So many problems. These are just a few problems I mentioned. Or make a gameplay, robotics, chess game. Chess game, again, training data will be good, but to generate a training data for playing chess game, oh man, it will take time. Because the chess, you move from one position and you go to different position. There's a different rules that you must move. And also the players are different. Some are kings, some are knights, some are many. So they all have their own rules of moving around. So most likely a chess playing game, are we gonna use the reinforcement learning? Most likely. So yeah, that's all we can say. Let me wait for a few seconds. Why we have so many problems? This is a very, I mean, not so many. Why we have so many algorithms? This is a very interesting question. One also we can answer based on my example, linear versus non-linear. So linear regression or neural networking, small or large data, k nearest neighbor or deep learning. Deep learning need a lot of data. Noisy data, oh, support vector machine is good. Every textbook mentioned that. As we said, only the support vectors, only few data make decision by the boundary. So the rest is there. Yeah, we'll see the examples soon. High dimensional data depends on the type of problem. But first, if possible, let's use a principal component analysis to see if we can bring the dimension down a little bit before we start. Yeah, again, we'll see more examples as time goes on. So the next session, we talk about the high level categories of machine learning. See, the concept is high level. We don't want to go detail. Again, we are spending like 30 minutes to 1 hour to learn all the machine learning algorithm. So as we said earlier, we have the supervised learning, unsupervised. Also, semi-supervised learning is possible, but most textbooks don't discuss it. So a semi-supervised learning means you have a training data. Some of them have the target variable, some of them didn't have it. Then reinforcement learning is common also. Assembly learning normally go with supervised learning also. Yeah. So this we'll go through all of them. Okay, so we start with the concept of what is a supervised learning algorithm. First thing with supervised learning algorithm is that we need a training data. That's why the first section we highlight learning from labeled data. Labeled data means I have a data about students who've passed a class, who fail a class. My training data means it's an historical data based on the students' attributes, their values. We know from previous years either they pass or they fail the class. So that will be our again, as we said, the training data, or here we say learn super. Actually, that's the term supervise. It's like a teacher or somebody supervising the whole. So we have a training data to again build them on. Yeah. So that's all we can say, unless if anyone want to add something to it. As I said earlier, you can ask questions at any time. When you speak, I'll just listen to you and answer your question. So supervised learning is like study with answers already provided. And that's our label data now. So for every example in the training data, the models show the input. Input, normally we use the term the features, and also the correct output, which will be our label. That's why we say label data. So input will be, for example, patient have disease A. The body temperature, the color of the eye, the blood pressure will determine if you have disease A. So our input will be those three items. Disease A will be our label or the known output. Then we can use for classification or regression. As we said earlier, classification means our label, the output, is a categorical value. Let's say true, false, yes, no. It can be more than two. Maximum, no, small, medium, maximum. It can be any amount, but yeah. Regression will be numerical value, like predicting the stock price or predicting a height of a basketball player based on his weight and what again? Based on his weight and some other features. So these are the examples, some few examples of supervised learning: linear regression, logistic regression, decision tree, k-nearest neighbor, support vector machine, and also neural network. So the last thing I would say is that supervised learning normally trains a model using the label data, where each example include the correct output, similar to learning with let's say like I'm learning with an answer key, preparing for exams. I have question with the answer key, learn. Yeah. Okay, so if no question, let's keep going. So now we're going to start with each of the algorithms. So the first algorithm we start with is what we call the linear regression. So regression is a very traditional statistics. It's been around for a long time. It's a statistics method. And normally we use it to model the relationship between, in statistics, we use the term dependent variable and independent variable. So independent variable will be what we know. So here in this case, independent variable will be the input, then the dependent variable will be the output. So in statistics, we have like a simple linear regression and also multiple linear regression. Before we do regression, we'll do what we call the correlation, because correlation will tell us if there's a relationship between what? The input and also the output. If there's no relationship between an input variable or independent variable and dependent variable, then if there's no any relationship, then one cannot predict the other. So always we do the correlation. This is the concept of statistics here. So what is the main goal here? Example is predicting continuous value. When to use linear regression. Regression, what we are predicting is a value, it's a numerical, quantitative. Yeah. So example, predicting a house price. And dollar amount is what? A continuous value. Or forecasting the daily temperature. Temperature is a value. Estimating a person's income. Income also is a value or continuous dollar amount. Predicting sales figures, and the list keep going. So here we say the strength is easy to understand. It's some kind of traditional method, very straightforward, and also fast to train, easy to understand, highly interpretable. Limitations: struggle with the complex nonlinear patterns. Here we are talking about linear. So nonlinear patterns will be difficult. So linear regression is the fundamental statistics or statistical machine learning techniques that models linear relationship between what? The output variable and or between the dependent variable and independent variable. Again, dependent variable will be our target variable, the label, and then independent variable will be our inputs. Yeah. Okay, so if no question, let's keep going. So next will be the logistic regression. Many textbooks already telling us, but we still calling it regression. Logistic regression is not regression, it's classification. We made an example about fertilizer. Fertilizer is good, yes or no. Yeah, a good example also is given disease diagnosis, yes or no. So this will be classification, classify as a disease, yes or no. But again, it's called regression. That's the traditional name that is given to it. So regression also is a fundamental statistics model, but primarily, or again, my English here, primarily is used for as we said, yes, no, true, false, for binary classification task. So that's why earlier I was saying logistic regression is classification. Yeah. Even despite its name, which include a regression, it's again it's very important or crucial to understand that logistic regression is a classification algorithm, not a regression algorithm. And we say what is regression? Predicting numerical values. Yeah, we don't have to. Doesn't have to be numerical values. Example will be as spam detection. Classify email as either spam or not spam. Or disease prediction. Determine if a patient is sick or not sick based on medical data. Customer churn also can be logistic. You can see all the example we are giving as classification because customer churn means we're predicting whether customer will leave or not leave the company, leave or stay in the company. Yeah, so that's what we mean by churn. Credit scoring also is still classification. We can assess if a loan applicant is good risk or bad risk. Based on that, either we can increase the interest rate or even deny the loan altogether. So it's classification. Also, same as regression, is very simple and interpretable. Output kind of probability concept. Also, it's limited to modeling complex boundaries also. Wait for a few seconds. So that's what we will talk. As we said earlier, you can see we are covering all the machine learning algorithm. The goal here is to understand the concept so that when we start our Python data science program with sklearn or scikit-learn, we understand the algorithm. When we mention decision tree, we know what we are talking about, but mathematically, not in this class. So let's machine learning class. Okay, so the next one will be decision tree. Decision tree, the main mathematics here is choosing the right attribute, the split. Normally we use the term, if I can, that term is something pure or not pure. Impurity or something. So what we mean by that is that, for example, I have a data set about, let's say about patients, and I take the age. And the age, I have 10 records, and we took age. And we found out the age, all of them the same age. Oh, that's very high purity, low impurity. So that is the correct data to split. The high impurity, which means impurity, let me use the word only impurity. So with the age, it will be low impurity. Now, high impurity means, let's say we are doing two classification, so 50-50. Age, either you are 20 or 30 years, and five of the patients is 20, another five is 30. So it means 5-5. But if all of them are 20, it means 10-0. So this means low impurity. Then we are going to choose that attribute. And there's a way we can determine that. That's the only mathematics here. It depends on the type of decision tree. Like we have a C4.5, Holmes, CAT, ID3, so a couple of them. And they all use the concept of like information gain, Gini index. Gini index also can be used. The whole idea is probability concept. Finding entropy also, you can find the entropy. Yeah. So that's what they mentioned first, the core idea. Split the data into branches based on decision rules. So splitting means I take one attribute, then I split it. The attribute content is age is 30 or 20. So I split it to 30-20 or true false or whatever they are. It depends on the content of the age. That's where you split it, go through. Yeah. Now they say, why is it popular? Easy to visualize. That one we agree with that. Very, very easy. Actually, easy to understand also. Yeah. So a decision tree again is a supervised learning algorithm that models the decision based on what? A tree-like structure. It's like a flowchart where each, again, we may have internal node represent a test on an attribute or a feature. And so attribute become a feature. Now, each branch represent the outcome of that test. And the last node, we use the term node, we call it the leaf. A leaf means a node with no children. That would be the final place to make final decision. So each leaf node will represent the final decision or prediction. Yeah. So we have a root node. Root node normally is same as data structure class trees. So normally in computer science, the root of the tree is at the top. In the real world, it's down, bottom, ground. So in computer science, we say the root node will be I'll use the term the topmost, because the root doesn't have no parent. So that's the topmost, representing an entire data set. Then we have the internal nodes that represent a test on a specific attribute. Internal node means you have a parent and also you have a children. But mostly we use binary tree like data structure class. Yeah, same concept the way that we visualize the tree the same. But here we are talking about decision tree. There's algorithm, as I said, something like using entropy, Gen index to select the correct attribute. So that would be the major mathematics here. So the strength here also, they say, is intuitive. Yeah, minimal, data preprocessing. Yeah. Also very easy to grasp. If you see the visualization, very straightforward. So interpretation is very good also. Limitation can be overfit if not control. And also sometimes one of the things we have to work on we have to prune the tree. Sometimes you get too much large tree and complexity will come in, time complexity, etc. And we have to prune the tree. There's a rules for that also. So that's all we can talk about decision tree. Or let's see if you have any question on it. Okay, let's go to the next one. So the next one is K nearest neighbor. K nearest neighbor, I would say that it's not a parametric. It's not a parametric test, but rather it's what we call the instance-based test. They use the term lazy. Some textbook may say lazy learning algorithm. Yeah. So I can't remember a data mining textbook was explaining this algorithm, and they say it works like you. There's a quote, and I want to quote it exactly, but it seems like I can't get the words together. But it's like, if you're a dog, you quack like a dog. So, again, I get the quote very wrong. I'm not good at that, keeping the quote. Dog quack like a dog. No, I'm not talking about DOG. I'm talking about DUCK. Quack like dog. If you're a dog, you quack like a dog. That's why it's called nearest neighbor. If we are similar, we'll be together. So they say the prediction is based on similar data points. So that's what I'm using. If you're a dog, you quack like a dog. You come together. Yeah, something like that. Yeah. So K nearest neighbor again is non-parametric. It's non-parametric test. Yeah. So this means that the K nearest neighbor makes no what? When we say a test is a non-parametric, or yeah, we talk about a model, or in statistics, we may have a test is parametric, a test is non-parametric. Next week we talk about that. No, next 2 weeks, 6 week. No, next week. Yes, 6 week is next week. So a non-parametric test, for example, sign test, or even Spearman correlation. With PSC correlation is parametric, Spearman correlation is non-parametric. But non-parametric, no assumption. No assumption. So we don't assume that the distribution is normal, the data distribution is normal. Yeah, that's what I can mention on that. So non-parametric means KNN or K nearest neighbor makes no any strong assumption by the underlying distribution of the data. This is taking us back to statistics, different between parametric and not parametric. So it doesn't try to fit K nearest neighbor doesn't try to fit a specific function like linear or polynomial regression line to a data. No. So that make it more flexible. So that make KNN more flexible. So who say one of the advantage of it? It's an instant base. Actually, instant base also we can use the term memory base. Memory base. So I would say unlike many other algorithms that build they normal like support vector machine decision tree, they normally build a generalized model from the training data set. Again, like support vector machine. K nearest neighbor, that's why we say it's a memory base. Normally it will memorizes or store the entire training data set. Then when a new query point comes in, that's where it makes its decision. Then directly compare the query to the store instance. So you can see the whole thing is memory based, yeah. Yeah, that's why the concept, the way it works, that's why again, there's no we say it's a non-parametric, no assumption about the distribution of the data set. Let's wait for a few seconds. Here, I thought this is the place I may get a lot of questions. In the previous semester, students asked a lot of questions here, especially the mathematical background. But as I said earlier, we can explain, but I can't go through the. I won't put it on a slide to explain, but I'll do my best to explain as much as I can. So let's wait for a few seconds if any question. Okay, so let's keep going. So limitation, we say slow for large data set because as we said earlier, it's a memory base. So it's going to memorize the whole training set. So imagine if the training set is very big and you give one query, you have to compare everything. So it's very sensitive to noisy data. So you can see the limitation, the way it works. That's why we have these two major limitations. Slow for large data set. If this large data set have a noisy data means there's error because you have to query it to affect the outcome. Yeah. Because again, as we said, the term lazy refers to the fact that the KNN does not perform any explicit training, no any explicit training, or model building. It doesn't build a model. There's no model building phase. All the computations, such as finding the neighbors, making prediction, is deferred until what? The prediction request is made. That's what I can say here. Yeah, or let's say no question. Let's wait for few. So normally a prediction request means we get a new data. This data have no, it's like a test data, no target variable. We don't have the outcome. So so it will be like query. So now you compare to the memory of the training. So if it's large data set, uh, it's not a good algorithm to use. If it's noisy data, oh, don't use it. Yeah. Okay, so if no question, let's keep going. Okay, the next one is support vector machine. Support vector machine is one of the powerful. Actually, that's why they say, why is it powerful? Let's look at that. They say it works well with high dimensional data. This is one of the wonderful algorithm. The wonderfulness of this algorithm is that it's very wonderful because you can have a very high dimension nonlinear, you have a nonlinear data set, and we have something we call the kinetic. So again, here we're not going to mention, if you take machine learning, they may go detail about it. So just the concept I'm going to mention here. But if you have a question, feel free to ask. So the kinetic can convert, take the data to the next level, the next higher level, and it can convert no matter how complex it is. It will make it from non-linear, take it to high dimension, make it linear for less, and you get your boundary, your classification. So that is kinetic. And as we said also, support vector machine is good for noisy data because only few data make the decision for the boundary. Yeah. So the only thing I would say is that support vector machine gain. It's a powerful, let me use the term versatile, that's one of the powerful English, no, not English, powerful word, versatile supervised machine learning algorithm. And it can be used for both classification and regression. You can use it for both for classification and regression tasks. So the whole fundamental principle behind support vector machine, as we said earlier, is to find a boundary. Now, finding the boundary, again, most textbook, I don't have a diagram, no diagram. So like what I'm trying to say is that you can find a boundary if you have let's say I have a two-dimension S and Y, I want to separate the two data. You can get over infinity boundary, infinity, the lines can be infinity. The goal of support vector machine is to choose the most, or to find the optimal hyperplane, the most best one, the optimal hyperplane. That best, I'll use the term the best, that best separate the data points of different classes in what? High dimensional feature space. The, this algorithm is very powerful. You learn about it. So optimal hyperplane is the one that do what? It will maximize the margin. You remember we said that the support vector machine, the goal is to get the classify the boundary with a maximum margin line. When you have a high maximum margin, chance of making an error is less. No, when I say error, I mean chance of misclassify is less. When it's a low, very close, when we say boundary line, let's say the difference between positive points and negative points are very close. So small change misclassify can come. So you want to get the highest, the longest boundary, the margin, the longest margin. So yeah, and it take two higher damage. That's one of the toughest algorithm. This algorithm was the developer is very famous from Russia. From Russia. See, sometimes Russia, man, they give us a lot of science, man. Let's go to chemistry. Mendeleeva table. I say Mendeleeva. How do you call it in America? You see, I studied in Russia. That's why I use the term Mendeleeva. I studied in Russia in the 80s, long time ago. Periodic table. Periodic table. That table, chemical table, chemistry, iron. It was a Russian man. But let's keep going. Let's keep going. Support better machines by, I think, Vladimir. Vladimir. The Russian people, they use that word. Vladimir means Victor. So they use that. Many, actually, Putin self is called Vladimir, if I'm not mistaken. But again, let's keep going. But you can Google it, support vector. Much. I wish we have time, like we Google it and look at it a little bit. Vladimir. Vladimir is a very common name in Russia, which means victor, victory, or victor in English, last name. So let's move on to unsupervised learning, if no question. So unsupervised learning, unlike the previous algorithm we went through, is on label. So which means we don't have a target variable. We don't have no target. The goal of unsupervised learning, majority of the algorithm is cross-story. Cross-story. So k-means, cross-story higher, we have partitioning, etc. But again, the goal is to cross-story. I think we use that term also in statistics a lot, is to break some things into two or more clusters. Items in the same cluster are similar. Items in different clusters are dissimilar. Here, most of the time, we use distance measurement to find out if two items are similar or they are not similar based on the distance measurement. Yeah, and we have many of them, like Euclidean distance is the most common. Manhattan distance. We live in New York City, but they have Manhattan. You see the way Manhattan is straight block by block. Yeah, so yeah, it works like that. Also, dimensional reduction can work. Anomaly detection. Actually, the idea of dimensional reduction here is that sometimes we may have a training data set, but we want to divide into any amount of, maybe let's say divide into two or reduce it based on some criteria. So we can use cross-storing and define the criteria, and we get two clusters, then we take one and leave one, something. So sometimes there are some job that you have to do cross-storing before you do your supervise, before you build your model. Yeah, but the process of cross-storing, the cluster don't know which variable is target variable or not. You consider everything the same. Yeah. Let's wait for a few seconds if any question. So again, unsupervised learning is a subfield of machine learning also. And as we said earlier, the main goal is finding patterns in data, not building a model. We don't build a model here. Because again, as we said, the data set is unlabeled. So the goal is to find patterns in data that has not been explicitly labeled or classified. So writing a query, I need all the customers from New York that age is over 30 years. It's kind of you are getting some categories of customers from the data set, but it's not cross-story because we know what we are looking for already. Here, we don't know what we are looking for. And that's the goal of the algorithm. Now, unlike a supervised learning, as we said, where the model learns from input-output pairs, a training data set, unsupervised learning algorithm are given only the input data, so we don't have no output or target variable. So the goal again is to find similar data and put them together as one cluster. The similar data will be in different clusters. So we say the task we can do here can be clustering, which is more common. Also dimension reduction, anomaly detection also. Some of the algorithm, K-means is one of the famous algorithm because very simple to implement or even to understand. Then higher ranking clustering, we have a DB scan, principal component analysis. We also have a density-based partitioning, so many of them. But here we're going to discuss these four major ones. So first one is the K-means. So the word is K. K means how many clusters we need. Then means the mean. We also have K median, which means you are the data is categorical. So you kind of take or you are taking your, no, not really categorical, but the means will be based on average of the centroid and the data point, but K median is based on median. You find the median of the data, the point and the centroid. Again, let's go through it. Unless any question, let's wait for a few seconds first. Okay, so K-means is one of the most widely used and well-known clustering algorithm due to the, as I said earlier, simplicity, easy to implement, and also easy to understand comparing to the others algorithm. So as we said, the K referred to the number of clusters we need. Yeah. And also the main idea behind K means K means weak, I say weak. K means works. I'm going to say work, not weak. K means work like interactive. Interactive. It's a process because every time we are going to update the centroid, find the mean of the point, put it in the right place. So it starts with the initial set of cluster centers. How do we know the cluster centers? Again, as I said, with the K-means, the first thing we do is to select the number of clusters we need. So if the number of clusters is 3, that means K equal to 3. We start with randomly 3 different points, which will be our cluster centers. And also normally we use the term, as I said, a centroid. Centroid. The cluster centers are called a centroid. And then repeatedly, that's why we say it's interactive. Repeatedly, we are going to refine these centers and the assignment of the data points to the clusters until we get a stable configuration, stable something that the update will not work. No, it will not update no more. Then we will finish. Yeah, very straightforward. So group data into K, then points in the same clusters are similar. That's all we can say here. And also the places that is used mostly customer segmentation, market analysis, image compression also. And as we mentioned, very easy algorithm. Comparing to the rest of the clustering algorithm, this is more simple and fast, easy to interpret. Limitation require choosing the number of clusters. So before you start, if I have to know number of clusters I want, we have some algorithm that the number of clusters, we don't need to choose it. So based on the algorithm, based on the data set points, last size, the algorithm is more flexible. The algorithm will choose the number of clusters for us, everything. So that's why this is a limitation. We have to do the number. Also sensitive to outliers. Yes, you have a very small data, very large data. So from the center to that point, it will have effect. Remember later we find a mean. Actually, that's why it's called k-means. Yeah. Okay. So next we talk about hierarchy. So higher ranking method normally represent, I would say that it represent a powerful class of algorithm that is normally designed to construct a higher rank of clusters or higher ranking of, I would say of clusters or models from the data. Yeah, clusters or model. Because we also have partition, which we are not going to discuss much. So we have the partitions like flat. So partition method like the k-means. K-means is partition. Normally require predefined number of clusters, as we saw the k-means. Hierarchy approach normally doesn't require the number of clusters, but rather it will build the term, let's say nested sequence of partitions, nested sequence of partition. Then from there, it can reveal the relationship at various level of the hierarchy steps. Maybe, let me wait for a few seconds, see if any question. The whole idea behind hierarchy method is to, again, as I said, it's hierarchy for, hopefully we understand hierarchy, from flat A to B, top. So the goal is to decompose a complex program into a tree-like structure, which again help understanding the inherent relationship or organization within the data. Yeah, we'll see example. Again, here we don't go data, but normally we can use the diagram which make it. For example, you can start with we have a method that first you're assuming that the whole data is only one cluster. Then you start to divide it based on some similarity. This you get two, three, you go. Or sometimes we say that all the data set, each one is a cluster. Then we start to combine. Two similar, we combine, then we get, yeah. So, kind of the whole idea. I think, let's say we have the visual can help us more, but again, we're trying to make things very quick here. No, 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 not quick. We're trying to just top view. Yeah. We don't want to go detail. Like the visualization will be better. Okay, so the next one is the DB scan. Again, wait for a few seconds if any question.
Are we taking a break? I'm not sure. Did we take anyone today?
Oh yeah, we'll take a break in a minute. I'm trying to see if we can finish these slides before we take a break. But since you asked,
Okay, thank you.
since you asked for break, let me pause my recording, then we take a short break. Okay, so we also talk about the DB scan. What is the also DB scans we said earlier is also cross story or unsupervised learning. So we say unsupervised learning, normally we have the dimension reduction concept, the cross story, and also anomaly detection, so can be unsupervised learning. Yeah. So this DB stand for the density base. So this is a density based cross story. algorithm. And normally it normally address the shortcomings of a traditional method. If I say traditional method, I mean a concept like k-means, which is partition hierarchy. Yeah. Here by defining the clusters as region of higher density point. Higher density point. So for example, I think I'll open again, we won't go through detail because otherwise we're going to spend a lot of time, but I just open one slice right here. What I want to show you is just the diagram. It should take few. So this is the concept of this is the different types of clusters we can have. A well-separated cluster will look something like this, which is very perfect. Then also we may have a center base also. Then we have the density base. Let's go straight to the. This is a density base. So we know this is one. Here we have one cluster, another, because density base means it will be very populated area together. Then it's a cluster. So that's what I want to show here, what we mean by it. So here we say cluster is a dense region of points, which is separated by what? A low density region from other region of a high density. Like here we have one, then we have a point here, then we have a point. So the green and yellow here is separated by low density, so it's two clusters together. So that's what we mean by, again, a density-based clustering. Okay, this is it. Okay, so the strength here is find the clusters of arbitrary shape, as we saw different type of shape. But also it's very robust to outliers since it's based on the density. So outliers will be maybe one single data that is very big or very small. It's not dense, there's no density there, so we ignore it. So that's why this is very robust to outliers. Limitation, of course, sensitive to parameter choices. Also struggle with varying densities, different type of densities also. Okay. So the next is a principal component analysis. Principal component analysis is used a lot. Actually, the is originated from linear algebra. Yeah. So the concept of hygiene vectors rotate. So the goal is again to reduce. So we just put it. What is a PC or principal component analysis? Normally, it's a linear, also unsupervised dimensional reduction techniques, and it's used a lot in linear algebra, as we say. Also, it transform the data, normally transform the data into what? A new coordinate system, such that I would say the greatest variance by any projection of the data comes to lie on the first axis. This is what we call the first principal component. And then the second greatest variance also will lie on the second axis, and we call the second principal component, the whole idea. Yeah. It's a lot of mathematics here also, eigenvectors. And here we say it's normally used in data visualization, noise reduction. Actually, the techniques is about reduction and faster model training, etc. Interpretability is very difficult. Most likely, we're going to lose some information. Yeah. This idea was in statistics, advanced statistics also. I think not mostly linear algebra, but it was PSC. Yeah, PSC, Carl PSC came up with this idea. So this is way back, maybe over 100 years ago. I'm not sure exactly the year, but it's over 100 years ago techniques by like PSC coalition. The same researcher came up with this PC. His name is Carl PSC. Yeah. Okay, so the next we talk about semi-supervised learning. So very straightforward. Some of the data is labeled and some of them are unlabeled. So here it uses a small amount of labeled data with a large amount of unlabeled data. So that's what we're going to say here. Why is it useful? We say that library data is expensive. Yeah, which is good. I mean, which is true because I want to get historical data of 100,000 patients who have disease A. Maybe I need to take some time. I mean, to take me some time, maybe some years to get that kind of data. And also, it also improve accuracy when labels are scarce. So we don't have the enough training data sets. So we'll put some on label inside, mix it with the labeled one, and hopefully we can come up with something better. So the common use cases is image classification also, text classification, web data analysis also. Wait for a few seconds if you have any question. Again, ask question, ask question. As I said about the Columbia University student and professor, always tell the student, ask question. If you don't ask, I'm going to ask. Okay, so the next one is the reinforcement learning. We almost finished. I think this is the last task. So reinforcement learning, the whole idea, I would say, maybe I may have a bias here, but it came from idea of, should I say, learning psychology, developmental psychology or something. It's like training a dog. So dog do good, you reward him some points. If the dog do bad, you punish him. The goal for the dog is to get the highest points. So if you punish him today, tomorrow if you tell him to do the same thing, he will not repeat the same thing and get the same punishment. So that's why we say it's an active learning process. Yeah. So reinforcement learning is very powerful framework for training, I would say for training agents. And the agent to make optimal decisions in a dynamic environment. Let me use the term dynamic environment. Yeah. So the key components we have agent, environment, action, and reward. Action is good, you get a reward. Again, we won't go detail here, but here we have so many couple of algorithm, how the process work. We have to even have a policy, how we update the values, etc. So, and also they have some concept called the SARSA algorithm, this concept also. The main application is robotics, game AI, autonomous system. Chess game also will be a very good also here. So the key idea here is, I would say, is try and error. The agent explore the different actions, then observe the outcomes. And again, as we said earlier, from there is going to adjust the behavior. I don't want to get punished twice in the same thing. Come on, I have to learn. Yeah. The next one is the assembly learn. I think we talked about that already. We have two major methods, which is the bagging and boosting. The goal of assembly method is combining multiple models to improve the performance. We may use two, like random forest means we use more than one tree. That's why it's called forest, maybe two or more trees. Yeah. We also have gradient descent, other boosts. This is the popular one, but we have a couple of them more. The benefits, as we said earlier, if I'm doing decision tree, I'd rather use random forest, higher accuracy, reduce overfitting. Because here you are not using only one tree, but maybe I'm using 10 trees. So the chance of getting the best out of the 10 or average altogether, maybe it will help. Yeah. So assembly method are machine learning techniques that again combine multiple individual models. Normally we use the term base learners, or sometimes they use the term weak learners, the data mining class, the textbooks. Yeah. The goal is to achieve a better predictive performance than if you use only one single model. Yeah. So why use assembly method? As we said, the benefit, improve accuracy, often achieve more. When you combine two or many algorithms to do something, you achieve more better result than if it's only single. Most of the time, I can say over 90%. Yeah. And many research articles tell us that also. Another goal is to reduce overfitting, so which means it helps to generalize better. Reducing overfitting means the system will generalize more better than. Also, I would say increased stability. Yeah, to increase stability, which means it's less sensitive to a specific training or initial conditions. Yeah. As we said earlier, the two major areas is the bagging and boosting. Random forest is also bagging. Yeah. Okay, so if no question, let's keep going. Okay, so here we also have the random forest. So that's many decision tree working together. The final decision is the aggregation of all the trees. So it's more robust, also handle large data sets, less interpretable than a single tree. So single tree will be better. In terms of interpretation, in terms of accuracy, again, random forest work better. Wait for a few seconds if it's okay. As we said earlier, decision trees, same as random forest, it can be used for classification and also it can be used for regression. Depends on the type we are using. And the last thing I'll mention in statistics, we have something called a bootstrap aggregating, and that's what we mean by bagging.
Professor, do we have this terminology in the book? I was just trying to find. This random forest terminology in the book. I couldn't find it.
Yeah, as I said the first day in the class, our textbook doesn't cover all the syllabus topics. So sometimes I may come with the slides or refer references. Our textbook is good for Python data science. So when it comes to NumPy, Pandas, machine learning, SKLearn or scikit-learn, data preparation, Wangly, those are the topics in the textbook. Maybe we'll go through that in a second. But when you look at the test, the syllabus, for example, next week, we have to cover statistics. Statistics like discrete statistics, inferential correlation. It's not in the textbook. But again, I provide a note for that. I hope I answer your question.
Yeah, Professor. Thank you.
Okay. Okay. So yeah, that's it here. Let's keep going. So choosing the right algorithm. We mentioned this also earlier. There's no one best algorithm. This also is discussed a lot in data mining, all this problem, choosing the right algorithm will depend on the type of problem, the domain, maybe engineering, medical, accounting, and also the size of the data. Is the data variable or not? Dimensionality of data also can have effect. Now, if you're doing supervised learning, should I do classification or regression? Sometimes I may have a numeric target variable as a value, but I want to do classification. Yeah, it's possible you can discretize the value into categorical. You can do that. If only you think that will give you a good solution instead of regression. Yeah. So here there's data science, data set size, the quality, interpretability. For example, if I'm doing some work for a lay person and I'm concerned about the interpretation of the outcome of the algorithm or the model, I will not use neural network. Maybe I'll use a decision tree. Yeah, decision tree, I can just visualize the knowledge, the rules I will generate. Sometimes also we have a rule-based algorithm whereby we can use the decision tree to generate the rules. Or we have something called the RIP algorithm to generate there are so many. Machine learning is a lot. But here we just summarize everything. So these are the key factors to consider. Business constraint also. Oh yeah, computational resources also is very important. Do we have enough resources to use maybe deep learning? No. Okay. Let's manage it with data science, decision tree then. Yeah. So no free lunch theorem. I like that one. No free lunch. No algorithm perform best for all problems. Yeah. And that's what we're trying to mention in the previous slide also. So performance will depend on the data, the assumptions, the problem context. What kind of problem we have. Yeah. Experimentation is essential in data science. Yeah. So you get better in data science with experience. Okay, so the next one is then what is naive Bayes? Naive Bayes is also a probabilistic concept and it's used a lot in data mining. We have two types. We have the Bayesian net and the naive means we don't consider, okay, that's right here, independent. Naive because it's assume independency between the features. We don't consider the features, the dependent. They don't depend on each other. Each feature is on its own. So that's what brings the word naive base. Then we have the Bayesian network. The independency is considered. Dependency is considered, that one. So the difference between the two. But what I would say is that they are probabilistic concept, algorithm for machine learning also, yeah. Wait for a few seconds if it's okay. Okay, let's keep going. Oh, okay. So the neural network we did into, so neural network is also a computational model. It's also a supervised learning based on human brain concept. So normally it consists of a input layer where we get the input, then we have a hidden layer. Hidden layer is where most of the time computation take place. Output layer produce the final prediction for us. So that's all we're going to mention here. This is more designed for complex patterns, especially if your program is very complex. We may have more hidden layers. Actually, many textbooks said if you have more than 5 hidden layers, then it becomes what we call the deep learning. Yeah, so the number of layers depends on the complexity of the work, of the problem. Yeah. So that would be the summary of what we machine learning algorithm again differ in terms of purpose and behavior. Here we are just trying to understand the concept that may help us. Hopefully when we do the hands-on in Python by next 2 weeks or so, we can select the right model, interpretation, etc. Mathematics comes later. Intuition comes first. But again, this course, we are not going to learn the mathematics at all. That's machine learning class, you're going to learn the mathematics. So let's wait for a few seconds, if any question before we stop. Okay.